Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 26. We are in lecture 12, and this is part A of that lecture, and we are discussing part 4 of sufficient statistics. Last time we discussed the sufficiency principle, which is the idea that if we have two random samples and we obtain the same value of the statistic, the sufficient statistic, from both samples, then the inference about theta, our unknown parameter, should be the same. So in other words, that statistic is sufficient to give us all the information we need to make an inference about theta. Okay. Then we discuss the alternate definition of a sufficient statistic, which uses the it says that the probability that x is equal to x given that t of x is equal to y is independent of theta. Then t of x, so if, then t of x is a sufficient statistic for theta. In this video, we're going to talk about the exponential family of distributions and some multiple parameters. All right, we'll see how far we can get in a reasonable amount of time. So the exponential family of distributions, the way that we know that it's the exponential family of distributions is we have to be able to rearrange how we write it in a certain format. Okay, so if it meets this format, then we can say that it is from a exponential family of distributions. So this includes distributions like the binomial, the Poisson, the normal, the gamma. Maybe the no, not the beta though, because beta doesn't have an e in there. So we have several distributions. Many of them can be written in this form. So what we have is we have a product of a function of x times a function of theta in the exponent, right, of e. And then we have plus a function of x only plus a function of theta only. And x is not dependent on theta. Now, this can be written as e to the kx p theta plus s of x plus q of theta. And we can break that up and say that this is e to the kx p theta times e to the s of x times e to the q of theta. And I can call this h of x, and I can call this c of theta. And then I have this general form that's not in the book, I don't believe. And we have a vector theta that goes from theta 1, theta 2, up to theta d. So there are d of these. And we're saying that there are k terms where we multiply a function of theta times a function of x. And d has to be less than or equal to k. So in other words, k, we have to have at least k terms here. And that has to do with linear independence, so that we have at least enough terms to handle our d parameters. Okay, and so this is a form that you would run into in many other textbooks. It's a more general form. This is a more specific form and simpler. So the authors tried to choose the simplest version. But I don't want you to be confused if you go to grad school and you see this more complex. I want you to understand the relationship between them. Okay, so our first example is the Poisson distribution. F of x is of the form e to the negative lambda, lambda to the x, x factorial. And so the trick here, to get it into this form, this is the form that we need it. But you can see where this form might be a little easier sometimes to see without as much manipulation. But it's good for you to know this manipulation. We don't see, everything's not raised to the, everything is not the exponent of e. So how do we make this whole thing an exponent of e. We take e and then we raise it to this power, the log of this power. And so by our properties of logarithms, if you remember, log base e of e to the u is equal to u, whatever u is. And so we're just going in this direction now. We're going in reverse. So that's an extremely important property. This is an extremely important technique, or you can't do this type of problem. So we're doing that, and then when we have e to the log of something, the log changes this into summation. So to make it easier to see, I wrote it as exp and then used the brackets here. And so when I take the log of this, I wrote this one first, and no, I didn't. What did I? Oh, I wrote lambda to the x. That's right. So e to the negative. Oh, no, I didn't. I wrote the first one. Yes. I have too many markings here. Let me clean this up, and let's zoom in a little bit. So I can write this as e to the log of e to the negative lambda plus log of lambda to the x plus, or minus, because it's on the bottom, minus log of x factorial. Now this term is negative lambda log e, and this is log base e, so this is still not very clear because I'm not zoomed in enough. So this would be negative lambda log base e of e. That is 1, so this is negative lambda, and that is what I have here. And then this second term, we pull the x down to the front, and so we have x times log lambda here. And then this third term, we can't do much with it. It's just log of the x factorials. And so that's what I've left here. Now, according to our form here, our format, if you want to think of it that way, we need a function of x times a function of theta, in this case lambda. We need plus a function of x only. That's pretty easy to identify. That's the x factorials, the log of the x factorials. Now we could write this as log x1 plus log x2. Oh, no, it's log of x minus 1, sorry. So we could expand this out, but it doesn't do us any good. So this would be x plus log of x minus 1. It just make it harder. Plus log of 2 plus log of 1, which is 0, just in case. So we could do that, but it just doesn't help anything. It makes it more messy. So we're going to leave it like that. And then we have a function of lambda only. That's this one. So that's our q of theta. So we've got those two. And then it's very nice. We need a function of x times a function of lambda. So this is our k of x times p of theta, or lambda in this case. And don't forget your support. And so we have now written this. Let me clean this up. We have now shown that this is a exponential. Therefore, the Poisson lambda is an exponential family, or is in the exponential family of distributions. So I may ask you whether or not something is in the exponential family of distributions, because it's real important that you know this. We're going to go over a theorem that's even easier than the factorization theorem. And so if you know that they're in the exponential family, then then you can use that theorem. But you have to show that they're in the exponential family. So you have to be able to rewrite these as an exponential family. So let's talk about the normal and we have mu 1. We did this last time, an example of that, and found that x bar is the sufficient statistic. If x bar is a sufficient statistic, then the sum of xi's is certainly a sufficient statistic. Okay, so for an individual x, there's only one value. We're talking about a PMF, not a joint PMF here, and this general form is for the joint PDF or PMF. So we have sigma is equal to 1, so our f of x mu, no sigma because sigma's 1, is equal to 1 over the square root of 2 pi e to the negative x minus mu squared over 2 times 1, which is 1. And then again, we do the same thing with this constant out here. We take e to the log of it, okay? And so I can rewrite this as a 1/2 power. So this is e to the log of 2 pi to the negative 1/2. That's another way to write this, okay? And so we've used our technique of e to the log of the constant, and we've changed the square root to a 1/2 there. And then the rest of it was already raised to the e. And so now we can add these. I'm going to write it as exp so that it's easier to write, and we don't have to write so small and wonder whether we're in the exponent or not. And so the first log of 1 is going to be 0 minus what's on the bottom, which is log of 2 pi to the half. And then I have a minus here of x minus mu squared over 2. And so this went away because it was 0. And so I have minus, and then I bring the half down in front of the log. So I have minus 1/2 log 2 pi. I don't need to expand that anymore. And then I have this quantity here, which I can pull out the negative 1/2 in the front, and then I expand this. But I need to expand this to get it in the form that I'm looking for up here. Remember, I need 3 terms. And so to get those 3 terms, I've expanded this. Now this is a part of S of X. This is part of it. It doesn't have to be all of it, as we're going to see here in just a second. But it's going to go with that because the constant, we could have only the constant, and then we could say this is times x to the 0 to get it as a function of x. Okay? So, and x is, our support is here. And so we can, I've rearranged this to, let's see, how did I get rid of the 1/2? So I think this needs to be a 1/2 here for the log of 2 pi. That can't go away unless I don't see any place where it could cancel out. Okay, so that was a mistake. Sorry about that. And so I'm going to here distribute the 1/2 across all 3 terms, and I have a negative 1/2 x squared. I have a negative 1/2 times a negative 2, so that's going to be a positive 1 x times mu. And then I have a negative 1/2 mu squared. And then this was negative, so I put it at the end by itself, negative 1/2 log of 2 pi. And so we need a 1/2 in there. So the x times mu is the k of x times p of theta, or p of mu. The constant and the x squared over 2, the negative x squared over 2, this can be s of x, and then minus mu squared over 2 is our q of theta. And therefore, the normal distribution is in the exponential family of distributions. Okay. Now, thinking about what we're doing here, the beta distribution may be in the exponential family as well, but we'll have to see. All right, so now we're going to do, this is the Bernoulli distribution. And so it's p of x, p to the x, 1 minus p to the 1 minus x. So even though I don't have an e here, I just take e to the log of all of that. And then I write it as exp. And so this becomes exp, and I have log of px plus log of 1 minus p to the 1 minus x. And then I take the x down in front of the log, which is what I have here. I take the 1 minus x, so I have to use parentheses there, times the log 1 minus p. And then I'm going to distribute the log, actually, across the 1 minus x here. So this is going to distribute across there. And so I get x log p, missing the g there, plus 1 times log 1 minus p, minus x times log 1 minus p. And so now I have, what I can do here is I have x log p plus log 1 minus p. You could leave this, you could just say that this is, and there's a p there. You could just say that that is, see, no, we have to rearrange this because we need, we don't want that together, actually. What we're looking at is this term and this term have both x and p in them, so they have to go together. And so we have x log of p, so I have x log p minus x log 1 minus p. I can factor out the x, and then I have log of p minus log of 1 minus p, and that's equal to x of log p over 1 minus p, using our properties of logarithms. And that's what we have here, and that is our k of x times p of theta, where theta is equal to p here. And then q of x is equal to the log of 1 minus p. Q of theta is equal to log of 1 minus p. Now s of x is equal to 0 times x. That's a function of x, and it's 0. So we could write 0 and say that it is plus 0 and say that that is s of x. Okay? So this means that the Bernoulli is in the exponential family of distributions. Okay. All right. In each of these examples, it would turn out that the sum of x is a sufficient statistic for the parameter. Why? Because this is the individual PMF, the joint PDF would be the product of these, and everything that's in the exponent is going to be summed. And so we would have here, we would have the sum of xi log p times the sum of xi. Actually, I should use the simplified version down here. So the final form. So let's look at the final form. We would end up with exp to the log p over 1 minus p times sum of xi plus n log of 1 minus p. Okay. And so we could break this up and use the factorization theorem, and we would have the sum of x, and that would make it a sufficient statistic. So you could do that with each of these through here and prove that to yourself. So this theorem is very, very handy. It says let x1, x2, and x up to xn be a random sample from a distribution with a PMF or PDF of the exponential form, which is given here, on a support that does not depend on theta. So you can't have something like x is less than or equal to theta. That doesn't work, okay? So you don't want that. Then the statistic sum of k of xi is a sufficient statistic for theta. Okay? And so the proof of this, the joint PMF or PDF of x1 up to xn is given by f of x1 xn theta equals the product, okay, of f of xi theta, and that's in this form. So it's going to be, everything up here is going to be summed, right? It's going to be exp to the sum of k of xi p of theta plus the sum of s of x plus the sum of q, oops, not g, q of theta. And so this is equal to, exp of p of theta times sum of k of xi plus sum of s of xi plus n times q to the theta. Here we have a sum and there's no indice. And this is equal to exp of p theta sum of k of xi plus nq theta times exp of the sum of s of xi. And so this is h of x1 to xn, a function of x only. And this is phi of u of xi, or x, 1 up to xn theta, which is equal to phi of the sum of k of xi theta. So this is the sufficient statistic for theta. Okay. So this theorem allows you to find a sufficient statistic for a parameter with very little effort. A lot easier than the factorization theorem in some cases. But again, you may have to rearrange the PDF to see if it's in the exponential form or not. Okay, we'll stop here and pick up with the example in the next video. Please make sure you come to virtual office hours. If you have questions, definitely come to virtual office hours. If you need help before office hours, by all means, email me. But when you email me, send me a picture of the problem, send me a picture of your work so far so I can see how you're approaching it. And as soon as possible, I will get back to you and try to help you through email. Please take care of yourself and stay safe because we want to see you here next time.